Alright, let's start by discussing the Kuhn conditions or KKT conditions, and in this lesson I will call it KKT conditions or KKT. Anyway, these are a set of necessary conditions that must be satisfied for a solution to be considered optimal in a constraint optimization problem. They extend the Lagrange multiplier method by adding the ability to deal with inequality constraints, which makes them particularly useful in nonlinear programming. And in simpler terms, they help us figure out the best solution to problems where there are certain limitations or restrictions. And KKT conditions are widely used in many fields. For example, they are fundamentals in operations research, where we aim to optimize costs, schedules, or resources. And you will also find them in machine learning, like in support vector machines or SVMs for short. And they are important in econometrics, control systems, and financial optimization. So having a clear understanding of KKT conditions is very important if you are working in these areas. And let's look at the mathematical setup for this kind of problem. What we are trying to do here is to minimize a function, which we call f of x. This function represents the objective or the thing we want to optimize, but there's a catch. We can't just minimize fx without any restrictions, and there are constraints we need to satisfy. And the first type of constraint is called an inequality constraint. These are written as like that. Here g sub I of x is less than or equal to 0, where I runs from 1 to n. Here you can see. And this basically means there are limits or boundaries that we can't exceed. For instance, if we are optimizing a budget, the inequality might represent the maximum amount we can spend. And the second type of constraint is in equality constraint. These are written as like that. You can see h sub j of x equals 0, where j runs from 1 to p. This means there are conditions we must meet exactly. For example, if we are balancing supply and demand, the equality constraint ensures that supply equals demand. And okay, and I think that's done. And let's look what's next. All right. Now we will look at KKT conditions themselves, and to begin with, for a feasible point, look at here, x star to be considered a local optimal solution. There must exist values for the Lagrange multipliers, and here you can see. And where are they? I'm looking here. These multipliers are important because they help us account for the constraints when solving the optimization problem. And the KKT conditions are made up several parts. And first we have what's called primal feasibility. And this simply means that our solution has to satisfy the constraints. In mathematical terms, this is written like that. You can see g sub I of x star is less than or equal to 0 for all I. And here you can see h sub j of x star equals 0 for all j. That means this. And these conditions ensure that the point x star lies within the feasible region defined by the constraints. Okay. Next, we move on to the second part. You can see here that it is called stationarity or the gradient condition. To understand this, we need to introduce the Lagrangian function. And the Lagrangian is a mathematical tool that combines the objective function and the constraints into a single expression. You can see here it's written like this. And what's happening here? Let's read it. Here L of x lambda and mu equals f of x plus the summation from I equals 1 to m of lambda sub I times g sub I of x plus the summation from j equals 1 to p of mu sub j and times h sub j of x. Okay. And what this equation is doing is balancing three components. And the first term, fx, is the original objective function we want to minimize, remember. And the second term here incorporates the inequality constraints using the Lagrange multipliers lambda, this. And here the third term does the same for the equality constraints using the multipliers mu here. All right. So now that we have the Lagrangian, the stationarity condition says that the gradient of this function must equal 0 at the optimal point. And mathematically it is expressed as like that. And let's read it. Here the gradient of f of x star plus the summation from I equals 1 to m of lambda sub I star times the gradient of g sub I of x star plus the summation from j equals 1 to p of mu sub j star times the gradient of h sub j of x star equals 0. This. And this condition ensures that the point x is a critical point, taking into account both the objective and the constraints. Okay, this theory is done, and I hope you understood. Okay, and here complementary slackness part. This is also known as the active constraint condition, and the idea here is to determine which inequality constraints are active at the optimal solution and which ones are not. The mathematical condition for this written as like that, you can see. And here lambda sub I star times g sub I of x star equals 0 for all I. And what does this mean in practice? Well, if the inequality constraint is strictly less than 0 at the optimal solution, then the corresponding Lagrange multiplier must equal 0. In other words, the constraint is not active and doesn't affect the solution. On the other hand, if the inequality constraint is exactly 0, meaning it's active at the boundary, then the Lagrange multiplier must be greater than or equal to 0. So this condition helps us figure out which constraints are influencing the optimal solution. Okay. And we will look at dual feasibility, which is essentially a non-negativity condition for the Lagrange multipliers. And you can see it is written like that. Lambda sub I star is greater than or equal to 0 for all I, of course. And let's talk what's happening here. Uh, this makes sense because the Lagrange multipliers represents penalties for violating the inequality constraints, and penalties can't be negative. If a constraint is inactive, its multiplier is zero, and if it's active, the multiplier is non-negative. And so now that we have gone through the conditions, let's quickly interpret what they mean in a practical sense. The stationarity condition ensures that gradient of the objective function is balanced by the gradients of the constraints at the optimal point. And the primal feasibility condition makes sure that the solution satisfies all the constraints. And finally, the dual feasibility and complementary selectness conditions make sure that only active constraints contribute to the solution. Together, these conditions form a powerful framework for solving constraint optimization problems. And where is we will talk about KKT conditions in convex optimization. If the problem is convex, it means the objective function is convex. The inequality constraints are convex, and the equality constraints are affine. Then the KKT conditions are not just necessary, but they are also sufficient for optimality. This is one of the reasons convex optimization problems are much easier to solve compared to non-convex ones. And we will look at a few special cases now. At the bottom, we have a little formula. If there are no constraints, meaning it's an unconstrained optimization problem, then the KKT conditions simplify the gradient of f of x equals 0. I'm talking about this formula. For problems with only equality constraints, the KKT conditions reduce to the classical Lagrange multiplier method. And in the case of linear programming, the KKT conditions align with what's known as the complementary selectness theorem, which is a key part of solving LP problems. Okay, and now we have an example you can see here. And what's happened here, let's talk. The goal here is to minimize the function. You can see f of x equals x sub 1 squared plus x sub 2 squared. This is our objective function and it represents what we want to optimize. In this case, we are minimizing it, so we are looking for the smallest value it can take. But we are not working without restrictions. There's a constraint which is given as like that, and x sub 1 plus x sub 2 minus 1 is less than or equal to 0. This means that sum of x1 and x2 can't exceed 1. So the solution we are looking for must lie within this boundary. Now, step 1 is to write the Lagrangian function here. The Lagrangian is a combination of the objective function and the constraint weighted by a Lagrange multiplier, lambda, and it is written like that. And what is that? L of x and lambda equals x sub 1 squared plus x sub 2 squared plus lambda times the quantity x sub 1 plus x sub 2 minus 1, right? This function captures both what we are trying to minimize and the constraint we must satisfy. Okay, step 2 is the stationarity condition. For this, we take the partial derivatives of the Lagrangian with respect to x1 and x2 and we set them equal to 0, as you can see here. And what is that? Partial L with respect to x sub 1 equals to x sub 1 plus lambda equals to 0, right? And the second is here partial L with respect to x sub 2 equals to x sub 2 plus lambda equals 0. These conditions ensure that the gradient of the Lagrangian is 0 at the optimal point. And step 3 is the complementary selectness conditions, and it's written like that. You can see lambda times the quantity x sub 1 plus x sub 2 minus 1 equals 0. And what this means is that if the constraint x1 plus x2 minus 1 is strictly less than 0, then lambda must be 0. But if the constraint is active, meaning x1 plus x2 minus 1 equal 0, then lambda can take a non-negative value. This ensures that the Lagrange multiplier only applies when the constraint is actually affecting the solution. And finally, fourth step is solve the system of equations by combining the stationary equations and the complementary selectness conditions. We can solve for x1, x2, and lambda to find the optimal solution. And it is x star. And the exact solution will depend on the specific problem, but the key idea is that these conditions guide us to the point that minimizes the objective function while respecting the constraint.